All right. So we're gonna keep, because we already are 8 minutes into this one and we got a lot of stuff to cover in here. I'm gonna try to go. So now you hear a little bit about resilient modulus this morning, and why it's important. You haven't get to that yet, but it is very important. It's very important because you're going to see that we have tried, many different groups have tried to do characterization of the material based on different things, based on deviator stress, based on shear strength, based on confining pressure. But in reality, when you put in here a load that is dynamic or Haber-Sign, a load that is a repetitive load, we're going to have not only the effects of the soil just due to the load itself, but also to the shearing behavior of your soil, all right? So I'm going to just show you the material stiffness characterization that we are using right now or currently in the United States on the latest mechanistic design guides. Not the 93, which is still used very widely by many countries, but and also in the United States, but by the newest AASHTO pavement design guide. And then we're going to talk a little bit about drainage of low volume roads. Like you see, the water is the problem, and we're going to try to figure out something. So I always say that the road infrastructure is a backbone for the nation, right? And rehabilitation and maintenance are very costly, very costly. And yet, we have no choice. We have to maintain the roads no matter what, okay? We have to spend that money, and that's something that, despite this huge spending on road rehabilitation, the current practice in the United States and in the whole world relies on a very empirical models, okay? Empirical means that you may get something that is fundamental below that, but you get few points in here from your area, and you put a line in there and you use it like it were the holy grail for the whole world, okay? Empirical models for the behavior of the subgrade materials are very widely used, okay? So if you go to the pavement engineering side, where we're trying to do all this geotechnical engineering, grade modeling, very and you go to the pavement engineers and they don't pay attention to the subgrade. They don't pay attention. They put a low value there, and then they design for the worst case scenario, the worst case condition, right? These models are used in many parts of the world, and that's the problem, because once you put a model in here and you calibrate with these conditions, everybody else is using without calibrating for local conditions. That's a problem. So this is important that we characterize the material in a mechanistic way. What I mean by mechanistic way means that it should be a model that should be applicable for everything. Then you get your data and evaluate the model based on your own data, right? Soil properties. But the fundamental things should be the same for everyone, not just an empirical model, okay? So environmental conditions play a very important role in the material characterization of the material stiffness. All these external factors that we see here, we were talking this morning about precipitation and temperature a little bit, but also is a solar radiation, relative humidity actually, which is one of the main factors for suction, and the groundwater table depth, obviously, wind speed, all of them are external factors that affect the pavement and subgrade conditions, right? All these internal processes that happen in the pavement are a function of some of these environmental conditions, not just only the load that you're putting there, right? Not only the load. So moisture gradients, temperature gradients, freeze and thaw cycles, drainage, infiltration potential, all of them have to do with environmental conditions, okay? And all of them are being affected the material stiffness of the soil. It's important. Okay, so why is important for pavement engineering that I do take care of the material's stiffness? We got put together a climatic model, and actually that climatic model not only take care of the moisture variation with the profile, but also the temperature variation. Temperature is important. Probably for us, it might not be important for some of the applications, but some of the applications, when you do have freeze and thaw cycles and thermal cracking, the temperature becomes a very important mechanism. So if we do temperature distribution within the layers, depth of frost and thaw penetration, freeze and thaw cycles, change in moisture and suction, and the environmental effects that you saw this morning, adjustment to the factor of the resilient modulus, we all affect the main distresses for which we design a payment system. I need you to understand that we do have very discrete analysis when we design for a bearing capacity for a foundation. We just have a number, right? Or slope stability, we got a factor of safety. Payment analysis is different. Payment analysis is a cumulative distress analysis, okay? So the way that payment engineers, and I'm not one of them, do is basically they figure out what is the rotting or permanent deformation with time and figure out how this thing is going to change, and they put a limit. And they said, at this time, my rod needs rehabilitation or fail, okay? And same thing for the rotting analysis, they do it for the thermal cracking, for the permanent, rotting, fatigue modulus, cracking and faulting for concrete pavements, and all of this. So it is a function of time. It's a function of time, okay? And you decide what characteristics you're going to call it failure or not. Well, we can do final element analysis, linear elastic analysis, and we have those permanent deformation modulus for unbound materials, and all of these are going to be a function of time, okay? And time are going to be a function of your climatic changing conditions, all right? So if you have in here the rotting going like that, the rotting is a function of resilient modulus, right? The resilient modulus is going like that. Resilient modulus is going like that, right? When you do have a lot of rain, your resilient modulus is going to go down. So that thing is going to go down a little bit and going to run parallel to this one, right? So, and when you get a resilient modulus increase, probably the rotting will, resilient modulus decrease, you got rotting increase, right? You know, and you're running here. So all of these will add up with time for the decision that you're going to take, whether the time will fail at 18 years or 15 years, right? And all of this is money. So that's how it works. That's very simplistic approach, but this is how we do for payment analysis and design. On top of that, we put on more, slope stability or road embankment stability and some other factors, but this is basically what we do for payment analysis and design, okay? So what we're going to learn today is the stiffness characterization, why it's important to be very clear on how to obtain that resilient modulus. And I'm going to show you some laboratory testing that we do for that, some field testing, and some empirical correlations if you have that proposal that you have to put together for, in 3 days, right? And you don't have the time to go to the laboratory to test that resilient modulus at optimum that I show you in the laboratory. So this is what we do. We test the laboratory, the resilient modulus at 1 moisture condition, maximum 2. You got resilient modulus at optimum or resilient modulus at a soak conditions, all right, at a soak conditions. And that way you use these values for designing, just everything. So we're going to show you these empirical correlations and some drainage considerations on that. So there are 3 means for determining the resilient modulus: laboratory measurements, field measurements, and empirical correlations right there. So we're going to go for laboratory testing right now, and basically what you want to do is to simulate a traffic loading, okay? And the test, we do it based on some measurements that Sid from California, Berkeley, I think, and his group of researchers in the 1960s postulated. That simulation is a repeated application of a deviator stress. Everybody knows deviator stress, sigma 1 minus sigma 3, right? That put on top on a confined on a specimen. So we're going to see that in a minute. Evaluating in a triaxial cell. Okay, so you had a large number of repetitions. I'm talking about 10,000 repetitions, right? Blah, 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 blah. Everyone takes in 1 second. You can just check. In 3 hours, you can get the test done. And basically, you change the conditions after certain number of repetitions. So I'm going to show you how. So this is the test. So you just basically impose, get a triaxial cell. You got a sample. I'm going to talk a little bit about that sample, and basically you put LVDTs to measure vertical deformation and horizontal deformation. And that's why pavement engineering fill these cells with air, not with water. We do it with water, right? But they do pour all these LVDTs around for lateral, for horizontal deformation as well, right? And they don't, and at that time, probably now there's some submergible LVDTs that are a little bit more expensive, but it's expensive, right? It's expensive to put those. So that's why they confine with air, because they put all these sensors right there. And they start doing loads, low repetition. And they do a lot of cycles, and basically the modulus is going to be your change in stress with respect to the recoverable strain that you get. In other words, you test it and you go up, and then you recover some. You go up and you recover some. And after 10,000 repetitions that the soil has equilibrated to that load, the last 5 repetitions, you measure the recoverable strain or resilient strain. That's why it's called resilient modulus, okay? The recoverable strain, and you use it and you get the resilient modulus for that particular set of stress condition, okay? So once the strain is measured, the process is going to be repeated for a combination of confining stresses and for a combination of deviator stresses to reproduce the different stress states of the soil encountered in the field. The data is then making a regression analysis. You're going to have one confining stress, sigma 3, sigma deviator, sigma 1 minus sigma 3, and you got a resilient modulus. And I'm going to show you got probably 28 or 30 different combinations. And then you put in a regression analysis, and you figure out what is your resilient modulus. Okay. There are 2 methods that are standard for doing laboratory testing. Have you seen that? Everybody taking payments in undergraduate? Okay, 1 or 2. All right, so there are a couple of test procedures. One of the most common test procedures that is used in the United States and in the world is the AASHTO T307. I'm sorry, you may have your own, but I don't have that information. This is called the determination of the resilient modulus of soil and aggregate materials, and it's been used forever. And the latest one is the NCHRP. NCHRP is for the National Cooperative Highway Research Program, and is the 128 harmonized procedure. Okay, I'm going to talk about the 128A because I think this is important. I'm going to compare a little bit with the T307 in here, but I'm going to be talking about the 128A, but it's the same as the other one. Okay, so you got the triaxial cell. Like I said, you put your sample. I'm going to show you the dimensions in a minute. You put clamps in here to put your LVDTs. You put horizontal LVDTs, vertical LVDTs, and you confine it with air, usually at a particular confining pressure that you need, right? And you apply your deviator stress. The specimen preparation is if you have an aggregate base, for example, for coarse grain materials, an aggregate base, you use a sample which is 6 inches, 15 centimeters diameter by 12. So it's a big guy, right? It's a big guy. And if not, you use the subgrade sample, which is 4 inches, about 10 centimeters, times 8 inches for that. All right. So those are the samples. So you have to have a couple of loading plates, right, at different sizes. This thing had to be manufactured for different samples there. And you put the samples at any assemble of triaxial cells. And then you applied what we call a Haversine load, Haversine pulse load. All right. When you simulate earthquakes, what kind of load do you use? It's the sinusoidal, right? Load. For traffic load, we use a Haversine load, and it's also a pulse, is a pulse. See if I can do this one in here. Is a 3 different load procedures depending on the material you got, and you got some time for this is time, and this is the load, and you have the seconds that you use, and you have one pulse that you use 1 second, and then you rest for 0.9 seconds, 0.1, and then rest for 0.9. And if you have the granular or subgrade material, you use 0.2 of a load and then rest for 0.8 seconds, okay? Depending on the material that you have. This is how we use the Habersign load. And you do that one every second for 10,000 repetitions for one load condition, okay? And then you repeat it for another 28 or 30 different. So the sequence of the loads. So how do you choose the sequence of the load? And that's very important. You need to minimize the probability of the test failure. Why? Because what you want to measure is the resilient modulus of the soil. You don't want to do permanent deformation, failure, kind of the shear strength, right? You want to load it to a point when you're not failing the sample, okay? Because you're going to have many repetitions on the same sample, right? So you don't want to fail it. So basically, if you just check any soil, right, any failure criteria for any soil, that's your failure line for this one. And if you use, for example, the classic approach that we had before, which was the T307, basically, you know, you got a confining pressure in here, and then, oh no, right here, and you start increasing the deviator stress, right? And you got stress paths that were this direction, all right? So what happened is, with the first confining pressure, probably after 5 deviator stresses, you're failing the sample, and you're done. And everybody's calling, why am I failing the sample? Well, because the stress sequence is not a right sequence, right? And you do that one for the next confining, and the idea was not to get close to this one, right? To finalize around here, but you never know what happened with the sample, okay? So this 128A sequence, basically what it does is uses a harmonized, a line of constants stress ratio, sigma 1 over sigma 3, which allows you to have this stress path, right? This stress path. And therefore, this stress path is a little bit more parallel to this. So you are varying in the next sequence, not only your confining pressure, but your deviator stress, right? And that way, you have more loads in here before getting into one that might fail your soil. So this is the sequence that we got, okay? And if you have, for example, a fine-grained material, the line of constant deviator stress will do something like that, right? All right. So there were, I thought I took this one out. Okay. I'm just afraid that I'm using the wrong, no, I hope not. It's too long, probably. There are different models. So you got all this data, right? You got 28, 30 different sequence, 30 different combination of loads. And you need to fit this information to a model, right? And there are, you know, since the 1960s, when Seed proposed this kind of sequence, there have been many researchers trying to find out the best model to represent the resilient modulus conditions, right? So you then use log models, semi-log, more complicated. They use 2 constants, you know, variables to constants to fit the model, fitting parameters, models all the way to about 6 different constants. They use different predictors, stress state, like bulk stress. What is the bulk stress? In geotech, we don't use bulk stress. We use usually, you know, sigma 1, right? Maximum sigma 3, right? We use that. Well, bulk stress, we use the 3 dimensions, sigma 1 plus sigma 3 plus sigma 3 plus sigma 2 divided by 3, okay? And the tau octahedral is 1/3 of the, okay. I think, I hope I remember. Tau octahedral is equal to 1/3 of a square root of the second invariant, right? Sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared, right? Something like that. So that's the second invariant. Those are the, so pavement engineering actually uses the three-dimensional thing because they have point loads for these traffic loads. All right, so, and they use this one, or they use independent variable like confining pressure, cyclic stress. We've been using many, many different models. So which one is the right model? And that, this is just few of them that I bring in here. Again, this one have all forms in which you include, obviously, the stress, and the response is the resilient modulus, and the K1, K2 are the fitting parameters that are a function of your material properties, right? So those are many, many models proposed in here. What I want you to see here, very carefully to see if you catch the problem with these models. These models have K1, K2, great, very stable, two parameters, but only they use the confining stresses. This one is pretty good for fine-grained materials, K1, K2 parameters. The less parameters, the best thing for you, but you have only the shearing stresses, tau octahedral, sigma 1 minus sigma 3, sigma, those are the shearing stresses, right? Doesn't include the confining pressure. Right. So now we get into the more universal models and more, and now we say, well, we need to include not only the confining stresses, but also the shearing stresses, right? So we got those two in here, and now they're a function of that, and now you have models that are called K1, K2, K3 models, because you got two more variables in there. And there are models that I said, well, this is a total stress analysis. I want something more effective stress analysis, right? In which I include my pore water pressure. So probably it's difficult to people measure pore water pressure on those tests, but at least I include a factor in here that, represents my pore water pressure, right? So there are models in there that are been trying to do, some is log scale, semi-log scale, and so forth, okay? But this has been the sequence of putting together those models to represent the data from the lab. This is the currently used model in the AASHTO MEPDG. Like I said, the laboratory is now regressed to these values, and your job is to put them, make a solver linear regression analysis, nonlinear regression, and find K1, K2, and K3 for that particular solver, right? When you do have your confining stresses and your shearing stresses ready. So K1, K2 model, I just bring one. I have like 10 different examples, but this one is the SEED model, the SEED and IDRIS, 1963. When they use the bulk stress, this model doesn't account for shear stresses, as I said. This one is another one that is the deviator stress. This model approach is good for cohesive soils, but at greater depth they don't consider the confining pressure. K1, K2, K3 models. The more common one is the universal model proposed by Witzak and Jacob Busan, and it has both. The P sub A appears in all of these models because this one will make is normalized, right? Normalized, and it's easy to model when you have a value from 0 to 1 instead of having values all over the place. So all of them use the atmospheric pressure to normalize the stresses of the soil. All right, so this one is probably the most common model on the K1, K2, K3. This one made it to the design guide. And for example, if you use triaxial test condition, your sigma 2 and sigma 3 are going to be the same, right? So your bulk is sigma 1 plus, it's not divided by 3. It should be divided by 3. All right. And this one is the tau octahedral. When you use sigma 2 equal to sigma 3, you default to this equation. This one, why? Okay, I need to check. Okay, so I'm not going to talk a little bit about, but what happens with those models is I don't see in any place that include the suction, all right? And suction is a fundamental stress state variable for the soil, right? The soil changes moisture content all the time. Suction changes all the time. Why we don't use suction on these models, all right? So they fail to do that, right? So these are models that And I bring in here something that, to me, I think is important that you understand how important it is. Like, for example, I'm talking about Harris sitting here again, 1967, when he shows the changing resilient modulus based on R value with water content. Look at the big change in water content. It's huge. It's huge change. And like, different, compaction conditions also is going to be changing, right? If you have this one on the wet, dry side of the wet side, but this is big changes. And there is a paper on the effect of moisture and freeze-thaw cycles and deviator stress on material stiffness from Willie Zhu in 2021. And he considered the important factors, and he considered a lot of tests and a lot of materials. And he found out that the density is very important for that. Then the soil properties, the WPI that I showed this morning, the passing 200 times PI. Then the water content. Look at the water content with the number of repetitions in the traffic. It's more important. He found it to be more important. And more important than the deviator stress by itself or the confining pressure by itself. But this is very important. If somebody is telling me that you've been checking analysis and the water content on the soil for a pavement analysis and decide is greater than the traffic load analysis, that's something. So it's very important. You need to consider that. So there are to be some suction-based models available from that. And there are many suction-based models. This one for the ones from the schools of Fredland in here have recognized this graph. And basically, if you have your groundwater table in here, I talk about my stress state variables that are fundamental. For a saturated soil, it's going to be my total stress and more pore water pressure, right? This is your effective stress. For the unsaturated soils, we can talk about the total stress, the pore pressure, and the pore water pressure, right? And then you can combine them in a way that you can measure them. You can use the three of them separately, or you can combine them, and that's what we did. We combined them in the net normal stress in here, which is the total stress minus the pore pressure, usually pore pressure 0 atmospheric, right? So that's your total stress, basically. And this one is your matrix suction that you've been looking at and very familiar now with that. Pore minus pore water pressure. So those are the stress fundamental variables for the unsaturated soil mechanics, or the negative above the unsaturated soils. So based on that, a lot of, this is, the models that you've seen include, most of them are total stress analysis, when you have only sigma 1, sigma 2, and sigma 3 total. When you get into the saturated soils, then you don't have any suction, right? The only thing you have are your effective stress, sigma 1 minus sigma water, which is your sigma 1 prime, right? Sigma 2 prime and sigma 3 prime, right? The effective stress for that. When you jump into the unsaturated soils, then you're going to have not only your net normal stress, but also you're going to have your suction applied to the three phases, all right? So this one is the stress state that we deal with in any unsaturated soil. And for triaxial conditions, again, and this is okay. For triaxial conditions, sigma 2 equals to sigma 3, and then you just get into your total stress analysis. You have your equations in terms of total stress. For the saturated, you got in terms of effective stress, which is 3 times your pore water pressure, right? Because you have sigma 1, sigma 2, and sigma 3. That's the tau octahedral for that, which is the same shear stresses. Whether you have water or not, you're going to have the same stresses, right? And the unsaturated condition, then you're going to have your net stress, which are your total minus 3 pore air pressure, your tau octahedral, which is the same, no matter what the water is, and you're going to have your suction value. So those are the stress conditions that we deal with when you have unsaturated soil, all right? So methods that incorporate the suction, I found many methods, but I think I divided into 3 different categories. One of them are those that use the effective stress from unsaturated soils, okay, which I don't like it at all, okay? I'm the school of, I don't like effective stress for unsaturated. I hope I convince you that, the suction is independent, right? It's independent of your external loading applied, is the environmental load. So Bishop proposed a model for that was very empirical in nature and was very popular. This is the first model that people start using, but it's inaccurate for the degrees of saturation less than 85. So you can use them probably good for saturation more than 85, but it's attractive for implementation processes. This is the model by Bishop, and it's very close to an effective stress, right? You have your net normal stress in here, like your total stress, plus your suction value multiplied by the famous Bishop chi parameter. Okay, and that chi parameter is a function of degree of saturation. So now we got a material that should be independent, also a function of suction, which you have the suction here, so it doesn't make sense. Okay, because you have now a sole property that is a function of the stress that is represented, right? Should be independent. So I don't like, but Bishop is good because what happened is, like, let's say, for example, you are teaching, for those who are in the academia now, and you're teaching bearing capacity for something, and you have a soil profile in here, you have your groundwater table, and you ask the students, okay, draw a pore water pressure profile in here, right? And what they're going to do is, or what you guys and undergraduates going to do, you're going to do this one and 0 here, right? That's your pore water pressure profile. Bishop analysis, because of that, it's going to allow you that the pore water pressure is going to have a certain value in there, right? So with this thing, pore water pressure, you can create a confining pressure and effective stress pressure, like, before it was effective stress, probably, I don't know, something like that, and then just jump, lower because of the pore water pressure, but now you're going to have a little bit more because you have the suction value right there. So it's easy to implement, it's easy to show them that the effective stress will increase a little bit because of that chi parameter and suction parameter. Second model, second way of doing is a factor that considers matrix suction independent of the contribution of the applied pressure, and that's what we saw this morning. Resilient modulus at optimum condition plus an environmental effect, right? That's going to be your tutorial in here to figure out that. And it's mechanistic in nature because it includes now the two stresses that are, the externally applied loads and the environmental loads. It's a decoupled approach, and I put in red what I think it is, not that good, but it's relatively easy to use and easy to implement. That's the one that is being used in the Ashton design guide in the United States. We use the WITSAC model. These are the total and the octahedral external loads, and the environmental factor, as you saw, will represent the factor that, related to the environmental conditions, right? The third model is more fundamental and said, well, why we don't include the suction in the laboratory testing, right? Why not? Well, we can put a triaxial cell and actually measure pore pressure and pore water pressure. And we can do that, all right? Or we can put the sample at a moisture content, and then you have your soil water characteristic curve and you know what your suction is, right? So why we don't do that? Well, the apparatus is a little bit expensive if you want to put pore and pore water pressure, right? The triaxial cell, I don't know, sells right now for $150,000, right? But nonetheless, you still have a way to do a surrogate, like with water content, and figure out what the suction value is as you do. And we got a lot of work on this one. And we came out with this, actually, Palanivello is one of my dear Indian students, right, from India. And basically, he worked a lot in the lab on this machine, and he come out with the Z1, C2, C3, C4, K1, K2, K3, K4 models, right? He put Z values in there, but actually he put the net stress, the tau octahedral, and he included the suction in here. That's a fundamental model, okay? Now what you need is going to be on the regression analysis to find the 4 parameters. You're going to need a suction column, right? But now I hope for you it's not that difficult to get that suction column in there. all right? So this one is rigorous and mechanist, all right? Obviously requires laboratory testing for calibration because you need K1, K2, K3, K4, right? But requires final element modeling because you're going to need that value changing with the time and difficult to implement. So how we do that? Well, again, we use a triaxial testing machine. We had a dead end, high air entry value here. We measure the port air pressure also here, and actually we build up on the top cap, and we put a port air pressure and the port water pressure transducers in here, and we measure that, and we actually modify. We put the same harmonized protocol to do that, and just put it in there, and we just were able to get very nice values. Okay, this one is, for example, what happened with, we used that model for undrained material with the universal model that has been using R squared of 0.70. This one gets to 0.95. So you see that now the contribution of the suction in the model is now being reflected by improving the model a lot, right? So this is important that you understand and consider it being important. And this one is even better. This one is for the drain material, an R squared of 0.25 with the best model we are using right now in the whole world, all right? With this kind of models that we got R squared of 0.88, because suction is very important. All right. How to get K1, K2, K3 if you don't have a laboratory testing equipment like that, all right? Probably some of my practitioners here will be very interested to hear that, right? And there are some data that was used. I think Rahul was talking about the LTPP, the long-term payment performance test. This data is available for everyone to download, It's a big data from the payment engineering groups in the United States, and it has so many sessions all over the country. The nice thing about this one is they do have resilient modulus measurements in the laboratory. So you can get the data, and this is what von Quintos did, and in 1998, and some other people did, they have regressing coefficients for selected constitutive equations. They use the universal model mostly, and for different soil physical parameters. So they got all this database, resilient modulus, K1, K2, K3 from the laboratory. They got soil parameters, PI, Atterberg limits, passing 200, density, water contents. And basically what they did is they used that, this is the universal model, and they put together values, empirical values for K1, K2, K3 for that thing. Based on what? Passing 3/8, passing 4% of clay, liquid limit, optimal moisture content, and so forth. This one is for coarse grain materials. So they use compaction characteristics. For silty and fine grain material, they use percent clay, PI, water content. And they use K2, fine grain soils, they use more parameters. So they do have now, of course, this is now empirical, right? You need to be careful because you're going to be using soils that were not used for the calibration, all right? So you need to be a little bit more careful on that. But there are, like this, I can show you 10 different papers on different calibrations for that. So there are ways to use the K1, K2, K3 models for that. Okay, so this is what I got for laboratory tests. I hope you understand how we get the famous resilient modulus in here, right? And how we can modify those results to include suction values, which I think is important. Field testing, I'm going to go quickly on that. We use the application of deflections. Anybody of you have done falling weight deflectometer in here? Few, 2, 3, okay. This is the test we do. We use what we call a falling weight deflectometer, And basically, what we do is we use that one. It's a non-destructive test, and it has a plate, a loading plate. And basically, this is the little card, and you got the plating here down. And depending on, there is a size for this one. I think it's 15, 20 centimeters or 30 centimeters for that one. The lightweight is less than that. And you have the load, and you apply the load, okay, to this one. And then you just go. go and apply loads on that one. Every time you apply a load, you're going to have a deflection basin. Okay, so here is this, a drop in weight of the pavement surface from a predetermined height onto a loading plate with a diameter of, okay, 30 centimeters, right? 30 centimeters in here. And the magnitude of the load, this is important because this is how you estimate the sigma, right? The load that you're putting in that can be varying by changing the mass and the height of the drops. Okay? Based on that, you also install velocity transducers in that beam, and you mount them in a bar, and they measure the deflections that occur when you put the load in here. Okay? So obviously, the farther you get from that point that you apply the load, you're going to have less deflections, right? Less deflections. And this is what we call a basin. You know, you find out a basin, deflection basin for that. Okay, and if you can see, you can get that deflection basin into a model, right, or into a function. Okay, so once those deflection measurements are measured, you know the layers. You have to go to the field. You need to figure out what is the density of every layer, and you need to figure out what is the height of every layer. Okay, and basically what the program does is that back calculate what the resilient modulus might be by exactly matching what you observe in the field, the deflection that you observe in the field, with the deflection that you get with the resilient modulus that you get to get exactly that deflection basin. Okay, so that's what we call a back calculation. Okay, back calculation layer moduli of the pavement. And again, there is a whole lecture in here, or all the questions we use for that I'm not bringing in here. We also have portable falling weight deflectometers that are smaller in size, and they have different, you know, obviously they're a standard size for that, but they're also very affordable to get. Okay. So what are you getting after that? Usually the influence depth is approximately 1 to 1.5 times. So if you have less than that, you're going to have composite deflection. I'm not going to get into those details. But back calculation in a nutshell, if each layer is considered to be an elastic layer, that's mistake number one, right? If you have clays, they're not elastic, they're elastoplastic, right? But you consider elastic layer in theory. You consider that each layer is isotropic, has the same properties, and homogeneous, and all boundary conditions are correct. So you do have a lot of assumptions. But it is possible to iterate various combinations of modular until you get whatever it is. And obviously, it all depends on what values you start with. Those who model, you're going to see that the initial input parameters are very important, right? Because when you're getting more than 3 layers, it's going to be very difficult for you to do it. So you do several iterations until you find a perfect match between the theoretical and the measured falling weight deflectometer measurements. Usually you use sigma 1 and sigma 3, that's your deviator, so you're going to need the coefficient of lateral air pressure at rest. I'm going to get into that. Need density and the thickness, and then you can put all of these, and there are back calculated programs that are actually available, most of them online and free, all right? Modulos, MATCAMP, ILBAC, WestDev, Julia. I mean, there are many of them are available, and you actually put whatever you get, and you just get your resilient modulus for the field. This is obviously, field testing is much faster to obtain many data points, right? But also you have to deal with the variability of the system, and you need to have experience on getting these, you know, basins very well measured, everything. So I will say that this is more like an art than a science. But nevertheless, this is what we use all over the time, you know, falling weight deflectometer to measure resilient modulus in the field. This is very good because it's non-destructive, right? So there is advantages for that. The time and the cost is much less than the laboratory testing, obviously. And basically, and it's because you can do a lot of more tests in a little amount of time. Non-destructive, mean no disturbance or sampling on that one, so you got a lot of more money for the buck. So this is great. And obviously disadvantage, you cannot control the changes in the densities of the moisture contents on the field. And obviously the approach is linear elastic. The theory is linear elastic, and basically it doesn't apply for all the soils. So this is the second thing that you use to get the resilient modulus, at least the most, you can get it from other things. You don't have laboratory testing, you don't have field testing, but you need some data, okay? So we jump into the empirical correlations. Again, these are to be used with care, and you need to make sure that, those are preliminary analysis of a stuff like that. Okay, estimation of resilient modulus is obviously of interest when you don't have time. When you're doing a proposal to get, you have to put something, in a week, or that you need some numbers rather quickly to the design, or basically, you don't have the money, or it's a small project. And there are typical correlations, and probably you recognize some of these in here. CBR, California bearing ratio, is the most famous and actually used all over the world, okay, including the United States. Half of the United States or more than that use CBR instead of the resilient modulus, right? Our values, the structure layer coefficient, they use grain size and Atterberg limits, soil properties for that. Even they use classification to just get a number for that, okay? So CBR values, this one is probably the most important, and the one that you're gonna be, and actually again, this is what the design practice in engineering do all the time. They use CBR. They didn't bring the test of the CBR, the California bearing ratio, that you do is a test that you put some material in a mold, okay? And you test the deflection or the deformation at different loading categories. It's a measure of strength. It's not a measure of resilience. It's not something dynamic. It's a static test. So that's why I don't like it, okay? It's a static test, all right? Nevertheless, there are some information in here. For the Shell Oil Company is the one brought in 1960, very used. It's a linear equation. So you got the CBR value multiplied by 1500, voila, you got a resilient modulus right there, right? Equation derived from wave propagation tests, and you got the original data, at least you know what is the variability associated with that. This one is the U.S. Army Corps of Engineering, using in 1975. It has now a power equation, 54 times 100 CBR 0.71. Here is the data. You use data from Shell, from AASHTO, road test in Texas, and so forth. This one is the TRRL, the Transportation Road Research Laboratory. And this one perhaps is the best equation I've seen. Okay, 2555 CBR to the 0.64. And that was the adopted actually on the AASHTO Wear Design Guide, okay? When you put in the guide, I have a CBR value instead of a resilient modulus, that's the question that the program will use for that. There are limitations. I do believe, I want to bring that out, and I always found my payment engineering when I go to this one. CBR is an easy thing, and it's like the Terzaghis, saturated condition, right? It's been there forever, so everybody thinks it's the best thing to do. It's not, okay? It's not. It's widely used, so there is a lot of data, but it's a measure of shear strength. Again, I mean, we're talking about resilient, and I talked to you about the importance of not failing the soil, right? And now they're failing the soil to get that value for resiliency. So I don't understand that, right? It's not correct. Besides, CBR is based on, do not recognize the stress dependency on modulus, okay, as you increase the loads, and therefore I critique this to be inadequate. But a lot of people use, have to bring it in here because that's the first you're going to be looking at when you get into the practice. Layer coefficient, AI value, this is how you get the layer coefficient, is a function of the heights of this one. Is actually how you do that for the back calculation modulus. Okay, these are the questions that you use. Poisson's ratio, modulus, the height of every one of the layers, they're related with the structural layer coefficient, all right? This is, again, how we calculate these layers. This one is the equation that they use. You're going to have those equations available for you to use if you need that. This is the nice thing about this, and I got the reference as well. The R value, when the place where I live, we used R values. It's from the Asphalt Institute, 1982. The R value is also another test that you do in the laboratory. I didn't bring that in here, but this one is the adopted equation also for the AASHTO design guide. Correlation with soil index properties, very good for us because it's easy to get passing 200 and PI, right? And DCP, dynamic compenetrometer, because we use a lot of data in the field for that. So there are equations for that as well. This one is correlation, the CVR with the soil index properties, and then you use the CVR resilient modulus to get, resilient modulus. This one is actually the best we were able to do for the coarse grain materials. This is in the design guide. And this one is for fine grain materials also, a function of WPI. Empirical correlation, when you include also index properties plus the stress, you mix them and you do a big regression analysis. It's easy to do regression analysis. You include in here water content, bulk stress, a value that is depending on the soil type, and the GR is a value for gravelly soils in here, okay? Very empirical, right? Every time you see a number like 0.5, 2, 3, 4, think it's empirical, right? It's not fundamental, mechanistic. So be careful with that. Be careful with that. Those were created for a particular set of conditions, all right? But they're available. Coarse grain materials, fine grain materials, a function of PI, water content, sigma 3 confining pressure and deviator stress are there. So they got water content, deviator, and shear stresses, but it's empirical, right? This one is a little bit more fundamental, has a deviator stress in here, has two parameters. It's like K1, K2 parameters, right? Those are the questions that you get for that. Hyperbolic models, and it's more a constitutive relationship, actually. Fine grain soils, also they have equations for that, so I brought them all for your notes right there, right? Problem with these equations that are empirical in nature, they're a function of the data that is used to calibrate them, okay? You need to treat them at least with some of the data that you got. And the resilient modulus, again, is a mechanistic parameter and depend on a soil index properties and also the stress state of the soil. Okay. So that's what I got for resilient moduli. I hope you got a very good idea of how to measure that laboratory field, or some empirical conditions, that empirical correlations you still can use for that. Okay. Drainage considerations, I think this is very important because the whole thing about this is about the water, right? If you can control the water, then you can control probably many of these changes in the stress state, and therefore changes in resilient modulus that are undesirable. So I'm sorry, I didn't bring I got the reference at the end, but I didn't bring the reference in here. Sarin Ghetto. He said 3 of the most important aspects of road design are drainage, drainage, and drainage. Okay. If you take the water out, if you control the water out, then you're going to be controlling many of these things, right? So clearly show that the bearing capacity of any unbound granular material are affected by changes in moisture content. I hope we convince you on that in the last 3 days. For coarse grain material, because you have a more drainal conditions, is the effect is less significant. The change in resilient modulus is less, actually. But when you have dense graded, remember when you saw the granular material, I was talking about an environmental factor of 2. But when you have a dense graded material, then you do have more changes, more considerable changes. Why we use drainage in the subgrade? Well, we want to lower the groundwater table level, close to this one. You want the water away from your babies or your infrastructure, to intercept lateral load, okay, of the subsurface water beneath the pavement structure, and to remove the water that infiltrates on the pavement surface, okay. The biggest problem is when we have a slope, a road section, and the biggest problem is when we have sloping hills, right? And Professor Barat showed you here many examples on the first lecture, right, on how this is affecting not only regionally but all the world. Protecting ditches is probably very important, and I think this is the best thing. Although we were, discussing last night, I think over dinner, that it's almost impossible to maintain all the ditches, right, in a town, in a place. So it's difficult, but stop falling of material into the deep, aid the clearance, everything. All these ditches should be clear of any debris. And this is the first thing you need to teach. Almost time. I'm going to give you 5 more minutes in here. And so basically you need to get that ditch clean all the time, all right? Clean of vegetation, and this one will actually help a lot. Roads must have a ditch, okay? If the ditch is missing, pavement will be damaged. I'm talking about low volume roads, any roads that, you do have, a lot of water to get away on that one. And I'm going to show you that the problem is, the lack of ditch, you get the water in here, and you start getting deformation because you get water accumulated, all right? Not only that, you get the water into places that you don't want them to go. Let's say a soil that, changes volume, like we're going to see next, or a soil that are compressible and, you don't want water in there. Or simply you're putting the water on top of the pavement with creating the potholes and all the stuff that you don't want to happen. So surface drainage control is important. You can do it in different ways, like a crown section, like, trying to do that. Out of a slope, so basically get the slope in such a way that you get the water out. For this kind of, designs, you're going to need to make sure that you put in the water in a safe place. Because sometimes you do that one without taking care of this side. And basically you are creating something down the slope, okay? Or in a slope with a ditch, right? You get the in a slope with a ditch. Also rolling grades are important. You got all these low volume roads, right? And this is an unpaved road. And basically what they do is they do a rolling pass that is lowering than the road. Obviously not good for high speed roads, no more than 20 to 50 kilometers per hour. But this one, make this one, and then also they do on a slope going down, and they cover that slope with some material that do not get the fines out of it. And this one seems to be working pretty well, and is much cheaper than a culvert, right? Culvert is basically the best thing to do to protect this one, but to put culverts every once in a road below, maintaining that this one that doesn't get anything is complicated, okay? Practice to avoid, what you want this is the water out of there as soon as you can, okay? So you need to design ways of getting the water there as quickly as it gets rain, okay? Long sustained road grades that concentrate flows are not good. Discharging water onto erosive soils, unprotected soils, not good. High boiling grading, you see a lot of people that send the technician to the field or the inspector and said, okay, I want you to figure out that the grades are okay. And instead of, taking a proper slope grading, inclinometer level or survey, equipment, they just go and they say, oh, that's okay, okay? They just look at it and say, oh, that's okay. Sometimes it's not okay. So you need to do a good job with the grading. Okay. Modeling drainage benefit. Modeling is very difficult. Drainage is very difficult to put it in the model, okay? Because you don't know what's going to happen. You can do any model and say, okay, this soil will not get more saturation than this amount, right? And you can model something like that. But it's very difficult because you don't know where the water is going in the field, okay? But we can estimate some benefit of putting a good drainage in there. And Bernstein and actually and Serenketo got values like, for example, the number of repetitions in here, as a function of the strain. If they use that equation, they use one for a soil that is undrained over the soil that is drained, okay? They can figure out that, this equation shows that basically the strain that you get in here are going to be a function of, that's going to give you the benefit of having like the ratio, going to having the benefit of having the drainage system. So maintaining and improving the drainage system is perhaps the most cost-effective measurement on roads where inadequate drainage is the main cause of deterioration. So you got roads in there that got a problem with drainage. That's what you need to pay attention to, okay? Then if you need to get the water in and you now know how to model the water and trying to figure out what's going to happen with that, fine. But the first thing you need to know is to avoid the water in the first place, right? All right, you guys have any questions? Very general. I wish, I got more time, but I hope I give you with good questions for lunch. Yes? Yes?
Hi, Prof. Thanks for the great lecture. So I would like to ask, as you mentioned about environmental loading conditions, including the pavement soil mechanics. So how we can consider the effect of Philistine cycle for calculating the Brazilian modulus? Through this equation, we have not considered any effect which is going to affect the including the water, if means including the ice or something in that way. Can you explain about that?
Right, thanks for your question. So the question is, you've been talking about moisture variability in the soil, but what about frost, frost and thawing, which is also very important on the behavior of the, the stiffness of the material. This is a great question, and you're going to be here in the tutorial this afternoon. So you better be here because I'm going to be answering your question right there, okay? Yes, we should be including, didn't bring obviously how we include it, but I can explain you what we do for that. But yes, we do include not only the environmental factor, but at the time you put the environmental factor, okay, that environmental factor actually can change depending on the condition that you have in the field. What you're learning here today was the environmental factor for unfrozen material. But once you get the switch between the temperature to be, above zero or below zero, you immediately switch the environmental factor from unfrozen conditions to freezing conditions. And what's going to happen is, and I'm going to just talk to me very, very quickly, when the soil freezes, the effect that it has on the resilient module is actually shooting it up very high. Actually, the soil gets very stiff. And the freezing is not the problem for the resilient modulus, because if the soil remains frozen all the time, the resilient modulus is going to jump from 30,000 psi to 100,000 psi, 500,000 psi. The problem is, after the freezing, what it comes is the thawing. And when the thawing occurs, these are all the problems that occur, because that resilient modulus not only goes down to the equilibrium condition, but goes even lower than that, goes to half of it, all right? half of the resilient modulus we have, because now we got extra water in the system. So how do you accommodate that extra water? If the soil can heave, it was heaving during the frozen. Now you got less density material, less dense material, and you got what the pavement people talk about, the supersaturated situations. All right? And now your resilient modulus goes down, and then it starts recovering with time, right? All of this, what we do in the design guide, we put them very empirical, right? We put a number of the resilient modulus that shoots up and then goes down all the way down, that depending on the soil type, and then the recovering time is also considered that depending on the soil type, all right? But all of this can obviously be modeled on this one, but this one we consider the resilient modulus on this period of time to vary that way. And then when it becomes unfrozen, then you go with the right condition that you learned this morning. Great question. You know, I didn't bring this one in here, but you're going to see a little bit of how to estimate the depth of frost penetration and the free swelling, you know, mechanism in the after. All right, guys, I think we went through too long, so okay, we're not that bad. 10 more minutes. All right, so I'll see you in Convey after lunch here, 2:30, right? So I'll see you then at 2:30, and thank you very much. Any questions from here? All right, I know I'm gonna have somebody having questions later. All right, I'll see you then at 2:30.